to be denoted by this notation. This is the conditional probability that event A is going to occur, the probability that the outcome is going to fall inside the set A, given that we are told and we're sure that the event lies inside the event B. Now, once we're told that the outcome lies in the event B, then our old sample space in some ways is irrelevant. We have a new sample space and that will to occur, the probability that the outcome, additional probability that event A is going to occur, the probability that the outcome is going to fall inside the set A, given that we are told and we're sure that the event lies inside the event B. Now,
the outcome lies inside the event B.
That to occur. This is the conditional probability that event A is going to occur, the probability that the outcome is going to fall inside the set A.
Probability that the outcome is going to fall inside the set A. So probability of A occurring is probability that the event falls inside A, the outcome. Falls inside set A.
Given that we are told beliefs about what is likely to occur and what is not is going to be denoted by this notation. This is the conditional probability that event A is going to occur, the probability that the outcome is going to fall inside the set A, given
Probability that event A occurs is equal to probability that the outcome falls inside set A. Event A or set A?
To occur. This is the conditional probability that event A is going to occur, the probability that the outcome is going to fall inside the set A, given that we are told and we're sure that the event lies inside the event B. Now, once we're told that the outcome lies inside the event B, then our old sample space in some ways is irrelevant. We have a new sample space.
Outcome lies in the event B. Lies inside the event B. Probability A given B. This thing here implies that the outcome lies inside the event B. So probability of A given, if the event B is just like ABC, like this, then the outcome lies inside here. So maybe the outcome's this, maybe the outcome's this, maybe the outcome's this. You have like A, B, C, D, E, F, G. This is all the sample space. Then we know the outcome is in this set here, B. All this is kind of irrelevant. Everything that happens outside of it, just focused here. This is kind of almost like our new sample space. It's almost kind of like, yeah, we said like the probability of A is equal to the probability of A given sigma, like this, or omega given the sample space. So it's almost like the probability of A given B is equal to the probability of A given this kind of sigma or this like omega B thing, where kind of like this goes to this. It's interesting to where it isn't so drastic, like changing from this to this. It's like there's, this is like new notation and stuff. But if you go from, probability of A given that the outcome lies inside the set here, so to probability of A given, sigma B. It's interesting. Yeah, you're always conditioning on a set. This event occurred. You could also kind of simplify, and if you have like the probability of A given sigma, that's just equal to the probability of A. But if you have kind of like, you have B here, and you've got A. Yeah. Probability of A given B is equal to so B is kind of like the new universe. So yeah. Yeah.
Is just the set B. We're certain that the outcome is going to be inside B. For just the set B.
You need to go back to this kind of thing here where it's like the probability of, let's say like ABC given, A, B, C, D, E, for instance. So we know that the outcome is one of these. So, this is good. This is good. This is good. This is not good. And this is also not good. So this is good here. And these are kind of not good. Kind of fall outside the set. I want to go back to what I was doing last time about probability of A given B. It's like the probability of, how was I kind of doing this last time? Probability, we had kind of like a big set here and like a small set, and we had like equal size sets, and we had a small set and like a big set. How do these two things relate to each other? What's the overlap between them? If there's a lot of overlap, the higher the overlap, the higher the probability. Yeah, I like to use this notation a lot more. So maybe if we just take this picture here, maybe let's do like the probability of, it's kind of like in the same kind of sample space here. Probability of A given B, So in both we have the same kind of picture. So A is just like this right here. Maybe we could do it as the A, and B is like this. I don't like it as much when we're dealing with these abstract kind of pictures. I like the discrete case a lot more. It seems like it's making like a lot more sense, the discrete stuff. This is feeling a little too like abstract, you know? Probability of A given B equal to probability of, you know, let's say we have like 1. Going back to this, if A and B are both the same set, then the event B occurred, the outcome lies inside the set B. In this case, like we know the outcome's 1. So now if we know that the outcome lies inside B, what's the probability that it lies inside A? We know that outcome 1 occurred, so we know that outcome 1 occurred, so we know that it lies inside set A, so this is equal to 1. If we have the probability of, let's say, 1, 2, given 1, we know that event B occurred, the outcome lies in B, we know that the outcome is 1 in this case, so what's the probability that the outcome lies inside the set A? It's 100% because, yeah, we know it's 1. What's the probability that, say we have 1, 1, 2. So we know that the outcome lies in here. If it's a 1, then we're good. If it's a 2, then we're not. Having a bit trouble relating this to probabilities, though. Kind of seeing the direct comparison stuff, but not as much in terms of probabilities. Kind of have 1 and 2, and we know that we're in this case here. What's the probability that we're actually just here? Could be here. How do we relate them?
certain that the outcome is going to be inside B. For example, what is this conditional probability? It should be 1. Given that I told you that B occurred, you're certain that B occurred, so this has unit probability. So here we see an instance of the revision of our beliefs. Initially, event B had a probability of 2 plus 1, 6, that's 1/2. Initially, we thought B had probability 1/2. Once we're told that B occurred, the new probability of B is equal to 1. Okay. How do we revise the probability that A occurs? So we are going to have the outcome of the experiment. We know that it's inside B, so we will either get something here and A does not occur, or something inside here and A does occur.
So it's kind of like if you have like the probability of A given B, say it's like the probability of, let's say it's 1, 2, 3. I guess that's fine. Given 1. So this is our kind of new universe now. This is like, we know that we're in here. We know that the event's in here. So you basically like get rid of everything else. Actually, let's make this 2. So we know that we're in here. So we get rid of everything else. And what's the probability that we're in A? It's 100% because we know that we're 2.
What's the likelihood that, given that we're inside B, the outcome is inside here? Here's how we're going to think about it. This part of the set B, in which A also occur, in our initial model was twice as likely as that part of B. So outcomes inside here collectively were twice as likely as outcomes out there. So we're going to keep the same proportions and say that given that we are inside the set B, we still want outcomes inside here to be twice as likely as outcomes there. So the proportions of the probabilities should be 2 versus 1. And these probabilities should add up to 0 because together they make the conditional probability of B. So the conditional probabilities should be 2/3 probability of being here and 1/3 probability of being there. That's how we revise our probabilities. That's a intuitively reasonable way of doing this revision. Let's translate what we did into a definition. The definition says the following, that the conditional probability of A that given that B occurred is calculated as follows. We look at the total probability of B, and out of that probability that was inside here, what fraction of that probability is assigned to points for which the event A also occurs? Does it give us the same numbers as we got with this heuristic argument? Well, in this example, probability of A intersection B is 2/6 divided by the total probability of B, which is 3/6. And so it's 2/3, which agrees with this answer that we got before. So the formula indeed matches what we were trying to do. One little technical detail, if the event B has 0 probability, then here we have a ratio that doesn't make sense. So in this case, we say that conditional probabilities are not defined. Okay, now you can take this definition and unravel it and write it in this form. The probability of A intersection B is the probability of B times the conditional probability. So
I want to see if this makes sense. Probability of A given B. It's kind of like if we wrote like the probability of A given sigma, then it's kind of like the probability of A over the probability of omega. But here we have the probability of A given B. This is similarly the probability of B, because it's our new universe. And we only have B stuff. So it's kind of like it's B and whatever part is kind of within B and also in A. We kind of get rid of the stuff around B. Get rid of it. You only keep track of the A stuff that's in B.
This is just a consequence of the definition, but it has a nice interpretation. Think of probabilities as frequencies. If I do the experiment over and over, what fraction of the time is it going to be the case that both A and B occur? Well, there's going to be a certain fraction of the time at which B occurs. And out of those times when B occurs, there's going to be a further fraction of the experiments in which A also occurs. So interpret the conditional probability as follows. You only look at those experiments at which B happens to occur, and look at what fraction of those experiments where B already occurred, event A also occurs. And there is a symmetrical version of this equality. There's symmetry between the events B and A, so you also have this relation that goes the other way. Okay, so what do we use these conditional probabilities for? First, one comment. Conditional probabilities are just like ordinary probabilities. They are the new probabilities that apply in a new universe where event B is known to have occurred. So we had an original probability model. We are told that B occurs. We revise our model. Our new model should still be a legitimate probability model, so it should satisfy all sorts of properties that ordinary probabilities do satisfy. So this element I, all possible pairs of roles are equally likely, so every element in this square has probability of 1 over 16. So all elements are equally likely. That's our original model. Then somebody comes and tells us that the minimum of the two roles is equal to 0. Once that comes and tells us that the minimum of the two roles is equal to 0. What's that event? The minimum equal to 0 can happen in many ways if we get two zeros, or if we get a 0 and if we get two twos, or get a 2 and something larger. And so this is our new event B. The red event is the event B.
It's like the new sample space. Yeah.
And now we want to calculate probabilities inside this new universe. For example, you may be interested in the questions about the maximum of the two roles. In the new universe, what's the probability that the maximum is equal to 1? The maximum being equal to 1 is this black event. And given that we're told that B occurred, this black event cannot happen. So this probability is equal to 0. How about the maximum being equal to 2, given that event B? Okay, we can use the definition here. It's going to be the probability that the maximum is equal to 2 and B occurs, divided by the probability of B. The probability that the maximum is equal to 2. Okay, what's the event that the maximum is equal to 2? Let's draw it. This is going to be the blue event. The maximum is equal to 2 if we get any of those blue points. So the intersection of the two events is the intersection of the red event and the blue event. there's only one point in their intersection. So the probability of that intersection happening is 1 over 16. That's the numerator. How about the denominator? The event B consists of 5 elements, each one of which had probability 1 over 16, so that's 5 over 16. And so the answer is 1 over 5. Could we have gotten this answer in a faster way? Yes. Here's how it goes. We're trying to find the conditional probability that we get this point, given that B occurred. B consists of 5 elements. All of those 5 elements were equally likely when we started, so they remain equally likely afterwards, because when we define conditional probabilities, we keep the same proportions inside the set. So the 5 red elements were equally likely. They remain equally likely in the conditional world. So conditional on B having happened, each one of these 5 elements has the same probability. So the probability that we actually get this point is going to be 1/5. And so that's the shortcut. More generally, whenever you have a uniform distribution on your initial sample space, when you condition on an event, your new distribution is still going to be uniform, but on the smaller event that we considered. So we started with a uniform distribution on the big square, and we ended up with a uniform distribution on just on the red points. Now, besides silly problems, however, conditional probabilities show up in real and interesting situations. And this example is going to give you some idea of how that happens. Okay. Actually, in this example, instead of starting with a probability model in terms of regular probabilities, I'm actually going to define the model in terms of conditional probabilities, and we'll see how this is done. So here's the story. There may be an airplane flying up in the sky, in a particular sector of the sky that you are watching. Sometimes there is one, sometimes there isn't, and from experience you know that when you look up, there's 5% probability that the plane is flying above there, and 95% probability that there's no plane up there.
I'm looking forward to breaking this down in terms of, sample spaces and stuff. Maybe I can just do it real quick. I mean, it's like event A, airplane is event B. This is basically, what's like the probabilistic experiment here? I guess it's like 4 things. Like there's just like 4 outcomes of this probabilistic experiment. It's basically like A. This is weird. He's using like events when I feel like you could say outcome, like outcome A, event outcome B. But so I think he's kind of using those interchangeably, but it seems like okay, I guess they're not outcomes. They are like occurrences. I forget what he called it when results. Like results. Yeah. Okay, but this is just event A. We should just think of it as a subset of the sample space. So I guess it's probably better to write it down like flying and radar. I kind of want to write it not with like no structure at all. So it's like flying and radar. And we have like flying and not radar. And we have like not flying and radar. And we have like not flying and no radar. And so this is our whole sample space. These are all the outcomes that could happen. And when we're talking about, say, event A, airplane is flying. So event A is basically these two events here, these two outcomes. Event B is something is on the radar. So event B is like this here. So this is our sample space, and when we say the probability of A intersect B, that's just like the probability of this thing right here, of like this thing. Yeah. So basically, what's the probability of this thing? It's interesting though. I mean, we could write it like we were writing before, that like A is equal to basically this set here. Basically two things. It's like flying and radar, and flying and not radar. And B is equal to registers on the radar. B is equal to flying and radar, and not flying in radar. So we say, what's the probability of A given B? That's equal to the probability of flying and radar, flying and no radar, given flying and radar, and no flying and radar. So given B, so I mean, if we roll this outcome, then we're good. But if we roll this outcome, then it's bad. We would not be an A in that case. So if we just kind of like draw this out as like a sample space, then, you know, we had that green, like this is B, and then the blue is so the green is B, and then the blue is A. So we basically have this here, this overlap. It's basically just this thing. What's the probability of this outcome thing here? Probability of A intersect B. It's just the probability of A intersect B is basically just equal to the probability of this single outcome here. It's like flying and radar. So what's the probability of this outcome? It's weird that we can just look at these kind of independently and kind of compare them, kind of thing. So we actually only know the probability of sets of outcomes. We don't actually know. So what we're given is the probability of sets of outcome. We're basically given that the probability of A, which is equal to the probability of flying. It's like flying and radar and not flying, flying and not radar. So it's interesting. We're given the probability of just like the set, but we're not just given like the probability of, we're not just given like the probability of flying. I guess this is kind of like closer to the real world. Like we should actually get these kind of like, these are kind of the individual outcomes. Like you would think that we would get, the probability of flying and radar, it's equal to whatever. And say we would also get the probability of flying and not radar. We would get like the probabilities of the individual outcomes, but we're not actually getting that here. We're just getting a probability of like a set of outcomes here, and we're also given the probability of, we're basically just given the probability of A, and therefore we infer, like we just know the probability of not A because it's equal to 1. When you say 1 minus the probability of A, this is equal to the probability of sigma minus the probability of A. Yeah, it's just everything that's not, everything that's not A. So, yeah. So basically given this, and then we're also given the probability of like B given A, which is equal to like the probability of radar, something registers on the radar, flying in radar, and not flying in radar. This is like 0.99. And we're also given the probability of B given not A. Oh yeah, I actually wanted to write this down. Like the probability of, this given A is that we're flying. So it's the probability of flying in radar and the probability of flying and not radar. This thing is equal to 0.99. So we're kind of in this conditional universe, and the probability of this thing like inside this conditional universe, this thing relative to the conditional universe is 0.99. And in a kind of similar way, we get the probability of B given a complement. Yeah. Yeah, this is probably good as kind of like a 4x4 grid, 2x2 grid kind of thing, where we kind of have like flying and like not flying, and we have radar and not radar. This is our sample space. This is an outcome, this is an outcome, this is an outcome, this is an outcome. So we basically know that the probability of A, it's like we basically know that the probability of this thing is equal to, yeah, maybe like the probability of this thing here is equal to 0.05, probability that a plane is flying. And then here we have a probability that the plane is not flying, equal to 0.95. We just know that the sum of this is equal to this, and the sum of this is equal to this. And then we know that, like, B given A. So B is, okay. Yeah, I think it's kind of cool to see this 2x2 thing here. Flying, not flying. So A is this. This is A. And B is radar. This is B. I don't like this color. Okay. This is B here. So the probability of B given A. So given A, we're basically in here, and then we intersect it with B. So it's basically this right here. This ratio, this to this. It's 0.99, so that's quite big. Complement given A, it's that. Then we know the probability B given A complement. B given A complement. It's kind of like this thing here. A complement is this, so it's the ratio from this to this. So this is like 0.1 and this is 0.9. You know how we would draw this. It's weird. It's cool to see it drawn out like this though. I like to see this. Because this is where it starts getting abstract and weird. Okay, it's cool doing this. I will see you guys later. Peace.